Thank you very much for the introduction. Hi, everybody. Yes, this is the last talk before the beach, so I will try to be on time. Let's say that's very important, more than coffee. So the objective of this presentation is actually to give you some kind of overview, some flavors of a research field that nowadays we call antiferromagnetic spintronics, which has been booming for the last, let's say, 10 years, something like this, and actually where magnetic oxides are actually playing a great role, and this is why we're having this focus during this call. So obviously in this title there are two keywords. The first one is spintronics. So you've had a full lecture about spintronics, but in short it can be really seen as the study of the interplay between spin currents and magnetic textures. And on the other hand, most of the time what we like to do is to handle spin formation in magnetic system, typically. And of course, the second keyword is antiferromagnets. And antiferromagnets are actually these peculiar magnetic textures where magnetic spins are antiparallel aligned. And this has striking consequences. And the first one is there is no net magnetization. If you average out all those spins, then magnetization goes to zero, and therefore there is no stray field. So that makes them very robust, very silent. And what you have to know is that actually they stand as the large majority of magnetic materials. So in nature, antiferromagnets are quite numerous. And one other very interesting characteristic of those antiferromagnets lies in their dynamical properties, because their magnetic resonances, magnetic dynamics, is actually lying directly in the terahertz range, meaning that those magnetic textures, in principle, can be manipulated on the picosecond, sub-picosecond timescales. And then when we deal with antiferromagnetic spintronics, is basically when we try to apply the concept of spintronics to antiferromagnets, or in other words, how could we use the very interesting characteristic of antiferromagnets dealing with spintronic issues. And of course, on the fundamental point of view, there are a lot of very nice breakthroughs. It's very interesting, but we have also to consider the technological breakthroughs, because if we think of replacing the ferromagnetic materials by antiferromagnetic materials in spintronic-based information technology, we could definitely boost their operating system by orders of magnitude. So definitely there is a huge interest in this antiferromagnetic spintronics. So this is basically the outline of my presentation, so it's kind of straightforward. Of course, I will start with some generalities about antiferromagnets, some reminders most of the time. Then after, we will emphasize their dynamical properties, and especially focusing on the terahertz capabilities. And in the third part, this is actually where we're going to deal with spintronics and spintronic concepts, especially dealing with spin currents and antiferromagnets. Of course, the literature is quite large right now, and if you want a quick read about antiferromagnetic spintronics, to the best of my knowledge, the most recent review is actually this one, which I find quite nice to read. Maybe in 10 pages you can grasp the most of the essence of this field of research. So let's get started. As I said, this is a typical overview of an antiferromagnet, antiparallel alignment. And these kind of magnetic textures actually have been predicted by Louis Néel at the end of the 40s, theoretically predicted, and it's all based, of course, as you know, you need a negative exchange. The exchange between two neighboring spins need to be negative. And as we are dealing with oxides, and as you've been already told during the talk of Sophie de Brémond, the main mechanism is super exchange, where actually the exchange is mediated through the p orbitals of the oxygen between the two neighboring magnetic ions. So that's the main mechanism. And as I said, as in real life, most of magnetic oxides are actually antiferromagnets. So it's quite interesting. So, but of course, as you can see here, the magnetic texture could be quite simple. You can just think of two sublattices, one red, one blue, just antiparallelly aligned. But actually, if you think of the real life, there are a lot of types of possible arrangements, depending which neighboring atom is antiferromatically coupled to the other. So here you have the standard case of the ferromagnet, where all spins are parallelly aligned. But then if you consider that two of the spins are ferromatically coupled, but another one is antiferromatically coupled, where you have what you call the A-type antiferromagnet. So basically you have stacks of ferromagnetic layers which are actually antiparallel. Then there is the C-type antiferromagnet, when two of the neighboring spins at this time are antiferromatically coupled and one is ferromatically coupled. So you have lines of ferromagnetically aligned, basically, and then you have this plane, which are now in the, if you take the cubic lattice, which are in the 110 direction. And you have the very well-known G-type antiferromagnet, because in this case, all the neighboring spins are antiparallelly aligned. So we are very often dealing with this one. So already it makes quite more complex, quite more rich spin configuration compared to the ferromagnet. But on top of this, you have to consider that actually you can have magnetic domains, and the magnetic domains, and you have different way of arranging those spins, sorry. And then you see, if you take the example of the NIO, which is an archetypical antiferromagnet, which is a G-type antiferromagnet. So basically, you have all these 1-1-1 plane, which are ferromagnetic like this, and then antiferromatically coupled. But if you look at this, basically, you have 8 possibilities to stack them. So that makes 8 T domain. Okay. And among these T domains, you have 3 possible orientations. This is what we call the S domains. So all together. So if you are tired, it's a nightmare. And if you're optimistic, it's very rich, let's say. So today I'm being optimistic, so it's a very rich magnetic materials. But altogether, then it makes antiferromagnetic quite rich and interesting. So now, going back to how can we manipulate them? So that's one of the drawbacks if we want. Okay, once again, if you're optimistic, you say, well, it's great because they are very robust against magnetic fields. So very silent is cool, but also what is difficult is normally when you want to manipulate magnetic textures, the normal way is to use a magnetic field. But coming to the antiferromagnet, the problem is that the magnetic field is quite inefficient. And you have what's happening if you apply the magnetic field on an antiferromagnet? You're gonna have 2 kind of transitions. The first one, which is the spin flop, and the second one, which is the spin flip. And then, if you consider basically the magnetic energy, you can directly see or evaluate, let's say, at what field this transition will happen. So let me explain shortly what are those 2 transitions. So if you take what we call an easy axis antiferromagnet, that means that there is only one axis in which direction the spin wants to lie. Then we will come back to that a bit later. But the spins are lying in that direction, either up or down. This is the antiferromagnet. So the first transition is called the spin flop. Basically, you have to compete, anisotropy and exchange have to compete the Zeeman energy, because let's say if you apply the magnetic field like this guy is very unhappy and this guy is kind of happy, so they try to find some kind of arrangement together. So then to go back to antiferromagnetic to up-counted states. This is what we call the spin flop. And most of the time, these spin flops take care as the square root of the exchange times the anisotropy. And then you have another transition. Most of the time, we call this the spin flip. And this time is when we want to fully align the two spins. And this one scales with the exchange times the magnetic moment. But if you put a bit the number, if you take some examples, they are very high. For the spin flop, they are very high. They are tens of Tesla most of the time. So it's quite difficult to reach in a conventional electromagnet, for example. And here I take one example. It's a very famous chromium oxide, Cr2O3, which is antiferromagnet. And in this picture, what you see the contrast stands for 2 kinds of antiferromatic domains. So this is what we call 180-degree antiferromatic domains. So either they are like this or they are like that. Okay, so you have white and black. And then if you apply a field large enough, here 6.6 Tesla in this study, then you see that you change the contrast, and then basically you go from this to this configuration, and this time they can lie in 3 possible directions. So this is where you see the contrast. So this is an example of a spin flop transition. Spin flip, we can forget about that. Huh? We have to compete with the full exchange, so it's hundreds of Tesla. Okay, so that's one of the characteristics of the antiferromagnets. So they are quite difficult to actuate, let's say, with a magnetic field. And coming back for the same reason, they are quite difficult to observe. So what is this image, actually? So the question is what kind of technique we can use to visualize antiferromagnetic patterns. And the reason it's difficult, again, is because there is no net magnetization, no stray field, so some conventional ways such as the Mach magnetometry will not work very well. MFM is quite difficult also, so we need to have some techniques. So I will advertise 4 of them. There are more, but I will advertise the 4 main one. And if we look at this image, this is the first one I will talk to you about. It's what we call second harmonic generation. And second harmonic generation, you've heard a little bit of it during the last week, and you heard of it as the normal probe of ferroelectricity. Why is that? Because second harmonic generation is this principle is the following: you shine a light at omega on the system, which has some nonlinear susceptibilities, and it re-emits light at 2 omega, twice the frequency. So, or in other words, at lambda, a wavelength, and lambda over 2, the wavelength divided by 2. And let's say that at the leading order, what we say that this is only allowed in non-central symmetrical systems. So if you have a breaking of central symmetry, such as in ferroelectricity at interface, it's very efficient to do this. But okay, that was the normal way we discussed SHG last week. But on top of this, you can add other ingredients. So for example, you can add the time inversion symmetry. And what you have to know is that magnetism, to some extent, breaks the time inversion symmetry. So if you add this to that, to second harmonic generation, then you have access to antiferromagnetic, to magnetism, let's say. And this is why, for example, it has been used, second harmonic generation, to image domain in multiferroic, which are both ferroelectric and antiferromagnetic, such as the BFO, for example, because they naturally break the central symmetry. And on top of this, you can add some kind of time central symmetry, time inversion symmetry concept. And that was, for example, done in the pioneer work of Manfred Fibig, where they managed to nicely image. So this one is the ferroelectricity. This one is the coupling between ferroelectricity and antiferromagnetism, and they managed to deduce the antiferromagnetic pattern. So that was done in the bulk YMNO3, which is a well-known multiferroic. And a couple of years ago, we've done that, for example. It works also in thin layers, where you see that in the red and blue contrast actually stands for the antiferromagnetic domains in what I have not put here, but you have to trust me, which is a single ferroelectric monodomain. So this is to prove that actually we can directly access the antiferromagnetic vectors in using this SHG system. But of course, you can go beyond this, and of course, I will not detail that at all because it's not a lecture on second harmonic generation, but just to mention that right now we have been just talking about this term, but if you look at the possible source of light, there are many possibilities, and if you dig a bit among them, then you find some potential terms which gonna directly address the antiferromagnetism, and this has been, for example, nicely shown. So here you have the 2 examples. All this is work from Manfred Fibig. So this has been shown in CR203, so it's a more advanced way of doing second harmonic generation, but then you have directly access to the Néel vector, to the antiferromagnetic vectors. And here, for example, it's in the prototypical NIO. This is the same, with the nice thing here, you have directly access to the antiferromagnetic vector. So just to sum up on this one, it's a direct access to the antiferromagnetic vector. I like to say that several times because it's not worth the time. And on top of this, most of the time we do this with femtoseconds lasers. So for free, or almost for free, we can have this time resolve capabilities on these systems. But then some drawbacks is, of course, every system needs dedicated analysis. You cannot take one analysis for granted. Then if you change the symmetry, change system, then you have to go back to the group theory and symmetry analysis. And it's definitely limited by optical resolution. So that's one of the techniques. The second technique is, Karim just introduced it just before, is the NV center magnetometry. And here, the thing is, actually, you don't access directly the antiferromagnetic vector, but since you can sense very or extremely small magnetic field, then you can have access to some extent, for example, at what's happening at domain wall of antiferromagnets, or if there is a step. So you have to be careful, but you can get some information on antiferromagnetic materials if you are doing NV magnetometry, and actually it has been extremely powerful to study the case of antiferromagnetic texture in BFO, where actually associated to the antiferromagnetic texture you have a tiny spin density wave which produces this magnetic field. So this is another way. Kaim introduces already, so I will not mention more. And then there are two others, and there is one which is called this X-ray magnetic linear dichroism associated to photoemission electron microscopy, so XMLD-PIM. And so this one is a synchrotron-based technique. So the idea behind this one is that you shine X-ray light, but you shine it resonantly to some electron transition. And most of the time it's the 2p towards the 3d if you have some magnetic ions. The nice thing of this is then you have element specificity. So by changing elements, then you have to change the wavelengths, and then you can define on which kind of atoms which kind of atom you want to probe. And then so that's the let's say the X-ray part. And then if you do this transition, to some extent, you can have some photoemission of electrons, and if you collect that in a microscope, then you can do some microscopy of the photoemitted electrons. And then the last term, of course, is dichroism and linear dichroism. What does that mean? That means that the light has not the same property if it is shined with one linear polarization compared to the other. So if you collect the light and the intensity of if you collect the photoemitted electrons with respect to the linearly polarized light with one direction onto another, and you look at the contrast, to some extent, you can have magnetic contrast. And this is what I will precise a bit later, but also what you need to know is that you are also highly sensitive to crystal anisotropy, and this is where these techniques can have some drawbacks. And it has been anyway nicely done, for example, if you take this paper. So if you take here, it's NIO samples, and here you have two images. So either you tune the wavelengths at the oxygen edge, so you should not see any magnetism. You will see only some crystal anisotropy. And if you tune it to the nickel edge, then you can have both crystal anisotropy plus, to some extent, magnetism. But if you do a careful analysis, and this one is quite complicated because you need to rotate the sample in different directions, you need to do several angles for the incident light, but then you can identify some domains. And the nice thing is that, for example, it's very tiny, but then here they managed to identify some T domains, as I discussed at the beginning. And here, doing also a very careful analysis for different incidents of light, they managed to identify some S domain. So these are another possibility. And the last but not least, there are also a lot of magneto-optical effects in antiferromagnets. So here I put an old reference. They are full of detail of this, but it's quite complicated. There are a lot of them, so I will not go through them, but I will just advertise one of the recent study. And actually, in practice, because this is why we are interested, this is what interests us, that we see very well the T domains which are related to this crystallographic anisotropy. And this is, for example, an example where you have the pink and blue T domain orientation. You have two possibilities if you look at them, if you are perpendicular or in line with the T domains. So with this, I wanted to advertise 4 techniques. There are some others, more challenging, but as this paper is quoting, seeing is believing. So one of the challenges working with antiferromagnetics is to see them, and actually having techniques on which we can rely on to observe these domains is quite important. Okay, so now coming to the dynamics. So the dynamics, the idea behind those papers, actually, it has been done also by Kittel and this time Keffer. So the idea is that one of the sublattices will fill the molecular field of the exchange field of the other. So, and that will be the whole idea behind the high-frequency dynamics of the antiferromagnets. But for this, let's do a quick reminder in the magnetisation dynamics in general and ferromagnetic resonance. So typically, magnetisation dynamics is governed by what we call the Landau-Lifshitz-Gilbert equation. And this is this one. So basically, you have the time derivative of the magnetic moment, of the spin, what you can call it whatever you want, which is equal to 2 terms. The first term is actually a precession terms. It's the equivalent of the Larmor precession. And basically, what's happening, if you tilt the magnetisation away from its equilibrium, its effective field, then it will start precessing around it. So, and the effective field can depend on a lot of different contributions. So the dipolar field, anisotropy, exchange, and so on and so on. Then, of course, you have a second term, because then you will not process like this forever. Then you will finally relax along the effective field. This is the damping term. And damping term can be also kind of important, but we will discuss that a bit later. But now what you have to know is that here you have a little term which is called the ferromagnetic ratio, ferromagnetic ratio. And this one, its value, it's 20 GHz per Tesla for the electron spin. So if you consider only a ferromagnet where all spins are aligned together, then you have no exchange. Exchange is zero, it's minimized. And most of the thing you feel is the dipolar field, which is about 1 Tesla in ferromagnets, and anisotropy, which is, let's say, 0.1 Tesla, something like this, or even less. And then if you do this, typically you do 1 Tesla times 20, this I can do, 28, then it's 28, done. So basically, ferromagnetic resonance typically lies in the gigahertz range. But now, if you consider higher frequency mode, you can have actually high frequency. If you consider high kV spin wave, then you can have some high frequency resonance in ferromagnetic material. But you cannot have this for, let's say, the ferromagnetic mode where all spins process in phase. Sorry, so I wanted to go directly here. So now, if we consider antiferromagnetic resonance, then you go to two couple equations where you have to add basically the exchange field of one sublattice to another. Okay, and if you do this, then you solve the equation. You can find the eigenfrequency, and then what you have basically you have a frequency, a resonance frequency, which is scaled with the square root of the exchange times anisotropy. And this time the exchange in antiferromagnet can be in hundreds of Tesla. Okay, so then that means that it's directly in sub-terahertz and terahertz ranges. So this is really what makes the difference between antiferromagnet and magnet. And the nice thing, it is at k equal to 0 compared to the spin wave I've just mentioned before. So at k equals 0, we can excite antiferromagnetic resonance directly in the terahertz range. But it's not so easy to access. So the nice thing, so that was at the end of the beginning of the 50s. So the nice thing, actually, people use tricks to access this resonance, to see the resonance in antiferromagnetic materials. And the first one, of course, you can always consider antiferromagnetic material which have a very small exchange, like it was the case in these materials. And using this, actually, it was detected directly, like it's basically 1.8 gigahertz if we convert in normal unit. And this was nicely measurable at that time, and they managed to measure it in this material. And the other trick they use, actually, is that you can actually reduce the, instead of reducing the exchange, you can reduce the anisotropy. And what you can do that, again, in the CR203, just by heating up close to the Néel temperature. And heating up to the Néel temperature actually will reduce the anisotropy, and then they managed to detect also in band X this CR203 material. So that was the first proof of antiferromagnetic resonance after the proposal or the theory of Keffer and Kittel. And soon after, they managed to measure it in sub-terahertz and terahertz ranges in a prototypical material, but it was quite challenging at that time, but there are beautiful studies. And then, for example, here I give you some example in some well-known, so these one are not oxide but fluoride, but it's the same principle. They are also driven by super exchange, etc., etc. But if you look at them, basically here you have resonances in the sub-terahertz range. Here you have close to 1 terahertz, and for example, NiO and MNO, which are very well-known, it's also in the terahertz range. So it was nicely measured. It was nicely measured at that time. So there is another concept for the dynamic I want to tell you. It's actually, if you derive this, you can have different modes. So it's basically a two-case scenario. So there is the first one. I already mentioned it a little bit. This is the case of the easy axis antiferromagnet. Okay, the easy axis antiferromagnet is one of the simplest. Actually, it's okay. Not only you have the exchange which want the two spins to lie antiparallelly, okay, this we know, but then you have the magnetic anisotropy which want the spin to lie only along one axis. If you do this, actually, this is in this case that you have this equation for the eigenmode. Then you have two kinds of modes which are actually circularly polarized. You have one which is basically circularly left, and the other one which is circularly right polarized. So this is one case. But also you have another case that most of the time we always present this one, but the other one is also very important. It's it's the easy plane. So this time, actually, easy plane or hard axis. So this time, the magnetic moments, they don't want preferentially lie along one axis, but they want to lie in a plane. And this is also nice, and this is the case of NIO. This is why I want to mention it. So you have two modes. So you have one which basically will preferentially rotate in the plane and one out of plane. But that will make two modes which are actually at two different frequencies. So this one will be a low frequency mode, and this one will be a high frequency mode. And I say linearly, but actually they are highly elliptical, like with something like a ratio for the NIO of 50 or something like this for one and 200 for the other. So this is why we call them linearly polarized. But the nice thing is that they are not degenerated in frequency. There are two different frequencies. So this is the two cases you should keep in mind. But once again, here I'm talking about the K0 mode. So I mean that where all spins, let's say, are in phase, but you have all magnons which can be accessed to this. I mean antiferromagnetic spin waves, and I invite you to read this paper if you're interested, because of course all those modes have some special dispersion if you look at them in field or in K-space. Okay, so to illustrate this dynamics, so there are some very nice recent measurements, and actually this one has been done in a group of Hubert. I think it was 2010, and even if it's not so easy to measure, so what they have done here, they have taken a NIO, and to trigger dynamic, they will do that with a magnetic field. Even if the magnetic field is not very efficient, they do that with a magnetic field, but they do that with a pulse, a terahertz pulse of magnetic field here, and they will probe. Since it's a bulk crystal, they can use magneto-optical effect, but they will probe it with a near-infrared probe. And what they are doing here, so here you have the terahertz magnetic pump, which is here, which has a broad spectrum, typically from 100 of gigahertz to a bit more than 3 terahertz. And then with the second probe, the second pulse, they probe the dynamics, and this is what you see here. You see very nice oscillation on 1 terahertz. And if they Fourier transform this guy, then you see the magnon response of the NIO samples. And the thing you can have also here is that you can see the decay there. And the decay is kind of important because that will be the damping, that will be the way you will relax to equilibrium. And we need low magnetic damping. Why? Because the higher you go in frequency, the shorter will be your lifetime. And the lifetime also depends on the damping. So you want a low damping to increase the lifetime. Because if you want then to do some magnetic computing, then you want to have magnons which lives long. And this is the reason we need so low damping. And this is why we're also interested in oxide. Because in oxide, which are insulating, damping is very low, like this is the case in this NIO. So that was one of the examples. But the nice thing of this is that they can be manipulated coherently. And what they have performed after this, here you see the excitation. If they shine a second pulse in phase, then they can enhance the excitation. And if they're out of phase, it is destroyed. So this is really a nice piece of work, where actually they show that they can coherently manipulate these antiferromagnetic spin waves at terahertz frequencies. But of course, as I said, magnetic field is not usually the best way to manipulate antiferromagnetic materials. So then you can use some other tricks. So then for this, I will illustrate this with another work, which has been very nicely done. This one, what they are using here, it's a TM-FeO3. And the nice thing, they will use a pulse, but of anisotropy. And how they do that? They shine another terahertz light, but this terahertz, what we will do, it will drive some transition in the terahertz and change the population. And by changing this, you will change the anisotropy. And this kink in anisotropy, actually, will trigger the dynamics. And once again, I will not go through the detail of the paper because it's very, very rich, but very nicely what they do, they can nicely see the terahertz resonance of this material. So this really illustrates the fact that antiferromagnetic materials, they are kind of peculiar, and one of their main features lies actually in their terahertz capabilities. And since their characteristic lies in the terahertz capabilities, of course, the first question we can ask, can they be useful? That's one of the questions. And because if you consider as I said, ferromagnetic dynamics typically it will lie in the tens of gigahertz, so that means in the microwave range. But then the antiferromagnetic dynamics will lie directly in the terahertz range, as I said. So definitely one question, if we look at this graph, actually also shown by Sophie de Brion, so there is this gap where we don't have a lot of things happening around 1 terahertz, and the question is, of course, what role could play the antiferromagnetic materials in future ultrafast devices? For example, knowing that in the 6G range, they will address this sub-terahertz range. So maybe, of course, we will not have a full revolution of devices with antiferromagnetic materials, but they might play a role. And for this, we need to be able to handle them, especially in nanostructures. And this is, sorry, and this is where actually now we can wonder what could be the role of spin currents. Okay, and now I switch to the other part of this presentation, because now we are dealing with spintronics. So, as I remind you, spintronics, what I like to see it as the interplay between spin currents and magnetic textures. And what is a spin current? The simplest definition is current carrying a spin angular momentum. I don't know why there is electrical currents. I think I forgot to remove something. And the first things, actually, which has been shown, is spin polarized current. So already Michel introduced this to you, but I do a quick reminder. But especially in ferromagnetic metals, so since you have an unbalance of spin up and spin down, if you drive a current here, then you will have an unbalance in your current will be spin polarized, typically. So for example, in copper, which is not ferromagnetic, then the current is not spin polarized. But if you look in cobalt, iron, or nickel, then if you look at the Fermi energy, there is this imbalance. So this is typically what we call spin polarized electrical current. That was the first one we worked with, they work with. But now there is some more fancy spin currents, and the first one actually is some pure spin currents. And the pure spin currents, there are some materials where the spin up and spin down, they like to travel but in opposite directions. So this usually happens in some kind of material showing strong spin-orbit coupling where there is a spinol effect. I will talk to that a bit later, but Michel already introduced it. And there is the third part, which is also pure spin currents, and this will be important for us. Actually, they can be conveyed by spin waves. Because if you look at spin waves, then it's a magnon, and magnon can carry H bar, so it can carry angular momentum. So actually, the pure spin current can be carried by spin waves. And here is also very interesting, because actually, here you don't have any Joule-heating, because you don't have electrons, they are insulators, so that could be quite interesting. So this is the concept of spin current. Then the second concept, of course, is the interplay. And the easiest way of seeing the interplay is actually looking at the origin of spintronics, and Michel has already introduced this quite a lot, so I will go quickly, but it's only, for example, the concept of geomagnetoresistance, where the magnetic texture basically play a role on the electrical conductions, and vice versa, the electrical conduction can play a role on the magnetic texture by switching by spin torque. So that's really the interplay between magnetic textures and and spin current, spin polarized current. Okay, but the thing you need to know is actually that antiferromagnets were already used at that time. But actually, they were not used, they were used as passive element, because they were used basically to pin one of the ferromagnetic layers using exchange bias. But of course, the goal of antiferromagnetic spintronics is to wonder if we could use antiferromagnet as active spintronic elements in these devices, and especially to use their interesting properties, for example, the one of their dynamical properties. And they've been the first paper, actually this is, I think this is the pioneer paper, I think this is the first one. What they have done, they have replaced the ferromatic layer by an antiferromatic one. There's still this permanent layer, but they could see some kind of magnetoresistive behavior. So this magnetoresistive behavior is the direct sign that actually there is something going on with antiferromagnets. And this is where actually people start thinking of antiferromagnet as potential active device in spintronic device, active element in spintronic device. But as far as we are interested about oxide. So what about oxide? So there have been some very nice demonstration of conduction of spin currents through insulating antiferromatic oxide, and that this has really triggered the field of antiferromatic spintronics. And the concept is the following. So you have yttrium garnet material, which is a ferromagnet, fair enough. Then you have NiO, which is antiferromagnet. Then you have platinum, which is going to be used to convert spin current. And what people have done, they have driven the ferromagnetic resonance. And as you know now from the spintronic lecture, if you drive the ferromagnetic resonance, then you will emit a spin current. And then what they are doing, they are comparing if you don't have NiO and if you have NiO. Okay? And the first thing, actually the first striking thing, is that they can see a signal here at the platinum if there is an NiO. So this is a direct proof that something is traversing, is going through the antiferromagnetic layer. And it's small, but it's there. So, okay, this is what I wanted to tell you. So if you have a spin current here, and it can be converted into a charge current, this is what they are measuring there. But this, you already know that from the lecture on spintronics. And what they have done now, they have changed the length of the NiO, okay? And then what they could see a maximum. But this time, actually, after a couple of nanometers, they could not measure anything at all. And as a proof, what they have done, they have changed NiO by silicon oxide, which is not a antiferromagnetic material, and you can see then there is absolutely no signal. So this is really the proof that actually antiferromagnetic material, the NiO, could actually convey the spin current. Okay? That was one of the first proofs. The second one, which is very nice, which has been done at the same time, they are doing exactly the same, but except what they have done in addition, they have really checked the dependence in frequency. And with the dependence on frequency, what you can see, you can just look at the line width of the ferromagnetic resonance, and you can see that in case of NiO, actually you have a huge increase of the slope. And the huge increase of the slope, actually, this is an increase of the Gilbert damping, I already mentioned at the very beginning. And this increase of the Gilbert damping, it's a proof of an additional channel to carry away the angular magnetic momentum. So in other words, carrying away some spin current. So this is the same. This study has been very thorough. So they check a lot of things. So this is when the NiO is directly in contact with platinum and the YIG, and then inserted, for example, copper in between. And what you have to know about copper has a very long spin lifetime. So if you have a spin current which is going here, then it crosses copper without any problem, then goes back to the other NiO and can be detected in platinum. Then they have checked if they insert also silicon oxide, nothing happening. If you have only copper, they don't measure anything. And if you have copper, then an NiO, platinum, then they measure a tiny thing. So that was really a proof also that actually antiferromagnetic oxide can convey spin angular momentum. And since the oxide, the way to convey spin angular momentum is through magnetic excitation, so through the magnons. Yes?
Is there any scenario in which also the lattice can be carrying angular momentum?
Yes. Yes, actually, so there are very recent study, actually, where people are working not with the spin angular momentum, but the orbital angular momentum. And actually, they have shown that the YIG, actually, there is, it was also done on YIG. So there was, it's grown on the substrate, which is a GGG. And then they managed to transmit the information because they detected through the other side of the GGG. And then this goes through a phonon, basically. Yeah? So
Why is this irrelevant in this scenario?
in this scenario, yeah. Well, because then after you have copper, okay, and then in this case I think it was actually in the previous case it was amorphous, for example, and then this is very bad at carrying angular momentum. So we believe that you need lattice to, because you need anyway to have this phonon carrying this angular momentum, so with shear, etc., etc. So it's not so. Yes. No, no. So, but what is your system? So you have ferromagnetic material, NiO, and platinum. Yes. Okay. No. What that mean? That means that actually, because platinum is a spin sink. Okay. So platinum, the spin current which will enter platinum will be lost completely. Okay. So this is actually this is what they see here. Okay. You see. No. Okay. This is what they see here with NiO. Yeah. Because there is always platinum on top. Okay. And the NiO will not make the lifetime of your spin current longer, but it will just help to carry it to carry it. It will be a channel for the spin current, okay? But of course, the spin current in the NIO at some point has to have the characteristic. We'll discuss that a bit later. But the spin current in the NIO has to have the characteristic on the antiferromagnetic materials. You see what I mean? But it's not. It will not enhance. Actually, it's just like a channel. But you will see that just after this one. But this is another business you will see. Okay, so that was two very important studies for the beginning of, let's say, antiferromagnetic spintronics with oxides. Okay, so that was at the very beginning. And I will come back to your talk just a bit later. Okay, and of course, soon after, they said, but how come we managed to see something? Because we are so far from the resonance frequency of NIO. I've just told you that the resonance frequency of NIO was at 1 terahertz. There was another mode at 170 gigahertz, something like this. And here they've been excited a couple of gigahertz. So they are very, very far from their resonance frequency. And actually, there was this work from André Slavin and his co-authors. Actually, they tackled this one. And I said that, okay, fair enough, you excite this very far away from their two resonance frequencies, so you have the two branch, but it's not a problem. So, okay, you might excite, it's not a problem. It can be a kind of problem, but you will excite waves, but there will be evanescent modes, okay? They will just, you cannot convey them on microns, but there will be evanescent modes with a penetration depth which has this form, and then you have one mode, so of course, 240 for NIO, very good, it's written here. So you have one actually which has this length, which is the penetration length of 24 nanometers, the other one, which is 5 nanometers. Fair enough. But what you have to remind, what I want to remind you, is that those two modes are linearly polarized. And the linearly polarized waves cannot carry a spin current easily because there is no H bar. It's a linearly polarized one. So if you want them to carry things, you need to combine them, because by combining them, you know that with two linearly polarized them, then you can have a circularly polarized mode, okay? And then they made this little model, and this is what they say, you have some decoherence, etc. But the nice thing is that they managed to reproduce the fact that they saw at some kind of thickness a maximum of transmission. They managed to reproduce this. So that was, if we consider those two first papers and this one, that was really what has triggered the field of oxide antiferromagnetic spintronics. But of course, there was one question where actually, what is it actually? Is it really coherently excited, or is it incoherent modes, or etc. with the heat, for example, thermal magnet, etc. So there was this paper, which was actually kind of very recent, where they tackled this problem. And this time they say, okay, what we're gonna do is that we take one antiferromagnet, which is still NIO, sandwiched between two ferromagnetic materials, which have two different magnetic resonance. And they use X-rays just before, and they can basically probe either nickel here or cobalt here, okay? And that they excite this layer at its resonance frequency, and they looked if this one responded at the resonance frequency or something else. And as a matter of fact, they could see clearly that it was responding at the resonance frequency, meaning that you had some kind of AC spin currents at this frequency, already discussed by Slavin just before. And the nice thing, of course, because then they are exchange coupled, so you can always say, okay, there is something from the ferromatic material which trigger, but it's not a spin current which triggers the something in the NIO, and then since it's also exchange coupled on the other ferromatic layers, this is the same. So what they've done that by adding either a silver or a palladium layer in between, and they can still see something happening. So that means that the spin currents which are arriving here can go through silver easily because it has also a long spin lifetime, and then enter the second ferromagnet. So it's a kind of very subtle study that I don't master very well fully. So I invite you to read this paper because there is a whole discussion on the phase of this where they're actually putting the finger on what is going on. But the nice thing, if they do that carefully as a function of the thickness, they can find exactly what the other author has found also, that kind of optimized thickness where you have a maximum spin current. Okay, so let me check on the tab. Okay, that's fine. That's fine. Okay, next. So now we're coming back to a bit to your point, because in all the previous study they excited the spin current with ferromagnetic resonance. So you have a spin generator, which is a ferromagnet. You drive at the ferromagnetic resonance. It's a spin current, which is very far from the antiferromagnetic resonance. then you have a spin current. But you have another way of having a spin current. I don't remember if Michel talked about that last week, but you can use thermal effect. This is called what they call the spin-Seebeck effect. Then you have a heat gradient, okay, and because you have a heat gradient, you have an imbalance between thermal magnons, and then you have a magnons, basically a magnetic currents which goes through. So this is what they are doing here. They heat up YIG again, so then you create a heat gradient in that direction and also a spin-Seebeck effect. And this is the same what they did. Here you have the detector, as usual. If there is a spin current which enter there, it can be a charge converted by spinel effect, and you will take the charge. And this is what they have done just by as function of the field. And then you have a bare YIG platinum, and then if you add the NiO actually, and then you can see that you can find also a very nice dependence. And the nice thing is that if you put tantalum, which has the opposite spinel angle, that it is reversed. So this is the fingerprint of the fact that it's a spin-hole related effect. And there is a whole discussion here because, as you can see, this is enhanced. So we could say that, but if there is NiO, it is enhanced, but it's not so easy actually, because what they have done, they went above the NiO temperature, and you can still see some kind of enhancement. So there is not only the antiferromagnetic part, but there is also spin fluctuations, which help basically the thermal magnons to go through. So it's kind of tricky. But you see, it's about the same time. So all this work really triggered the field of the antiferromagnetic spintronics in oxide. But now we come, I would say, maybe to one of the major breakthrough. We come to this paper, actually, which has been done by Romain Lebrun in the group of Matthias Clauy. And this time, actually, they use not anymore a thin layer, but they use a crystal of hematite, which is Fe2O3, which is also a well-known insulating antiferromagnet. And they put two contacts of platinum, and one is basically triggering the spin current, and the other one, exactly like the previous study, acts as a detector by spinel effect. So what's happening if you drive a spin current, a charge current here, you will have a spin accumulation at the interface, and then you will trigger by spin torque. You will trigger some dynamics in the antiferromagnet. This is one effect, and the other effect is that you will heat up. And by heating up, then you have thermal magnons, and you will this time have a magnetic spin current through the detector. But the nice thing about this study is they managed to measure spin current on very long distances, microns, tens of microns. Okay, so now it's becoming very interesting because you can think of carrying the spin information via antiferromagnetic material on very long distances. So that was quite some breakthrough. And then to show that actually you needed a very nice control material, the same group actually, what they have reproduced, they have done that, but not this time on thin layer. I think that was thin layer. I need to check again. But the nice thing, they could check if there is a domain pattern, if there are different domains. And you could see that the spin diffusion length, and I mean the characteristic length on which you can convey the spin information, was actually highly dependent on the size of the domain, as if there are domains. So for example, if you take this one in a thin film, okay, this is the single crystal. Okay, this is written here, single crystal, and then this is the thin film with let's say large domain and very thin domain, and you see that the spin diffusion length is really decreasing. So that means that to some extent, having very large antiferromagnetic domain is very important if you want to carry the information on a long distance. But very recent, I would say there is another very nice paper which also target this, and they put the finger on something which is very important, and this is why I wanted to advertise it here. So they reproduced exactly the same experiment. It was also in Fe2O3. So that means that you have these two contacts, then you excite a spin current, you convey it through the antiferromagnetic material, you pick it up here, they measure the dependence with the orientation of the field, etc. We can go into detail of this a bit later, but it's not really the point. The point is the following. So what they have done, they have measured the current they detect as function of the temperature and for different spacing of the electrode. And by doing this, they could actually put these figures. And actually, what they have here, they have the decay length. Okay. Actually, this is the length, characteristic length of propagation of the spin information. And they plot it as a function of the temperature, and you see that you have an increase and then after a decrease. And the nice thing here, they're explaining in the following way. So you have to remember, you have in this kind of system you have the two linearly polarized modes. And if you do this, actually, you try to inject some angular momentum. So you try to inject some H bar, okay? And the two modes, you have two linearly polarized modes, and then if you want to have this H bar, then they will try to match the dispersion relation of your materials, and they are separated by some values. Okay, because then it is injected here, then it will be at different frequency. It will be for the same frequency, sorry, at different k vector 1. And then that means that since they have different k vector, at the beginning, okay, you have the H bar, but then they will dephase, and at the end, you will end up with no more spin information. And this dephasing will depend on how far are those two branches for those two modes, okay? And what is nice is at low temperature, those branches are kind of far, okay, fair enough. And then when you go up in temperature, they come closer to each other. So this is why you can convey the spin information on longer distances. And they explain this decrease because here, when you heat up too much, at some point you have too much magnon-phonon scattering, and then you killed again the spin information. Sorry. And what is nice in the paper, they really put the finger on the way you can convey this spin information. But the nice thing you need to know is that in Fa203, those two branches are close together. Those two branches are close together. But in NIO, I've been talking just before, those two branches are far together because then one which is at 240, the other which is at 1 terahertz. So intrinsically, actually, they will not convey the spin information on the long distances. So this is what I like a bit about this study. Okay, fair enough. But right now you say I've not really been talking about high frequencies. I've been talking about how to convey spin information through antiferromagnetic materials. So there've been this proposal. Sorry. It's also a work which has been done quite early, like 2014, where you hear me? Okay, thank you. Because where actually, if you drive directly the resonance of the antiferromagnet, you will have exactly the same effect as in a ferromagnet. I mean, they will drive a spin current, and this spin current can be charge converted into, let's say, a heavy metal. So that's been proposed by Chen, Ting-Ying, and Bratas in this group. And the nice thing of this, so it's really the equivalent of this. But the nice thing, it has been proven experimentally as well, quite recently. So what people have done, they have taken CR203 this time. So this time, it's an easy axis antiferromagnet. They have shown on the sample electromagnetic waves at 240 gigahertz. And then they look at it as function of field. Because as I said at the beginning, here you have the two degenerated modes, circularly left, circularly right. But as you increase the field, you have one mode which rise, one mode which decay here. And then basically, if you are 240, you think that you will you will cross the resonance at that field typically, okay? And what's happening, as I said before, in CR203, you reach the spin flop, and after the spin flop, you have the quasi-ferromagnetic resonance, and this time, so you go from here to here, and now you don't rotate, you rotate but 90 degrees to what it was previously in the normal phase. And this is what they measure. They nicely measure, actually, at a given field, they nicely measure inverse spinal voltage, which is the signature of the fact that a spin current has been injected into the platinum. The nice thing that it reverses with tantalum, which has opposite spinal effect. So this is a nice proof. And then to enhance the signal, they made some kind of hybrid channel, but this is not really the point. The nice thing is that they also see the mode in the quasi-ferromagnetic regime, where the antiferromagnetic material is flop. But as life is never so easy, it's a bit more complicated than what they thought. So it's not a direct proof of it, because they realize that actually the quasi-ferromagnetic mode and the antiferromagnetic mode have opposite sign. So meaning actually what you are doing first is that because of heat, you start populating the lower branch. Since it's at lower energy, it's easier to populate with thermal magnons. So basically you compete between two things. You compete between in-current thermal magnons. It's me, or there is something strange happening, yes? But I will not like this. I don't see why. Like this? Okay. Anyway, where was I? Okay, so basically the idea behind here is, yes, they do see spin pumping at sub-terahertz frequency. This is very nice, but it always competes with the in-current and ferromagnons. So it's a very nice experiment, but that was one of the direct proof. To me, it was on like maybe 2019. It's one of the first real proof of sub-terahertz spin pumping, let's say. And there is a paper about at the same time. I have the reference if you want. Okay, good. So now, but now, what about higher frequencies? Because now we study, let's say, in the sub picosecond, sub-terahertz regime. So now let's try to get at a bit higher frequencies. And there was this paper tackling this problem, but in a, let's say, a bit cumbersome manner. But what they've done before this, I was about to forget this stuff. A little interlude in the informatic world to understand what's coming next. So little interlude. So. What's happening when you shine light, a femtosecond light, on informatic materials? Then you will generate an ultra-fast spin current. I mean, it's a spin current, but on 100 femtoseconds time scales for different reasons, but one of them is that because you have an unbalanced population of spin up and spin down again. Okay. Then you generate the spin current. And this spin current actually can enter, again, a normal metal, and if it's a heavy metal, will be charge converted. But this time, it will do this on sub-picosecond time scale. And if it does that on sub-picosecond time scale, then that will be the source of a terahertz field. Okay, so there is this whole activity, which is now called terahertz spintronics, because you can generate terahertz field with terahertz spin current, typically. Okay, so it's a kind of important. So knowing this, those people, what have they have done? They have taken an NiO sample, they have NiO platinum sample, they have shown a femtosecond pulse, and they have measured if there is a terahertz light going through. Okay, and they say if there is some kind of proof of ultra-fast spin current. So this is what they have done. And this is what they have. So this is very nice. Huh? So nothing to say. They have a nice terahertz field, which reverses this time with tungsten, which has also an opposite spinel angle. So they have done a lot of tests. They have done the tests without NiO, etc. Without NiO, they have a little bit of it. But what you have to know here is actually that if they do the dependence on the polarization of the incident pump, they see a huge dependence of it. So that means it's somehow crystal related. And here, what's happening? It's a more complex effect. It's an effect actually which is some difference frequency generation, which generate not a little p like in optical rectification, but a little magnetization which is dynamics. And any kind of small dynamical magnetization is actually a source of spin current somehow. Okay, and this is what they see in this study. So okay, they have only NiO with platinum. If there is platinum is enhanced, some kind of spin current going through the platinum, but there is not yet any signatures of antiferromagnetic resonance, because they have only this kind of broad ultra-fast generation, which is actually due some kind of optical rectification from the pump. And very recently, there was another paper. This time they tackle the same thing. They do the same experiment on a different sample. It's still NiO, but it's in a different sample. And what they see a very nice oscillation. And if they Fourier transform this oscillation, they see a nice peak at 1 terahertz. To be honest, I've not really understood what is this second peak, and I think in the paper it's not really mentioned, but it's probably it will come later. But anyway, you have this very nice 1 terahertz oscillation. And on top of this, you have still a bit some kind of broader band. And I will go a bit faster. So the nice thing here is that compared to the other study, they don't have any polarization dependence. So it's really related to something else, and they explain it the following way. They're explaining that they did some ultra-fast diffraction this time. So what's happening is that when you shine light on the platinum, it will start expand, and by doing this, it will contract a bit the NiO, and the NiO is magnetoelastic. That means that if you change a bit this structure, if you put a strain on it, then by magnetostriction you will kick out a bit the magnetization, and then you will trigger some dynamics. And then they follow the whole dynamics, and they can basically model what's happening here. So it's a very nice, very nice study, basically having really the characteristic of the antiferromagnetic resonance triggered by ultrafast dynamics. So, okay, I come to some kind of some intermediate conclusion. Okay, so definitely we can transport information via antiferromagnets. So that's really the first brick of antiferromatic spintronics. Spintronics, we deal with spin formation. We can carry it via antiferromagnet. Definitely, we had some spin pumping at sub-terahertz frequencies, and now there are some evidence of ultra-fast spin generation of a spin current in NIO. Okay, but of course, what is still needed in our field of research is a real assessment of what kind of magnon when you transport the spin information in these antiferromagnets. Okay, last part. I will do it quick because it's been already 1 hour, and you are all waiting for the beach, myself too. Okay. I will be very quick. I will just give you some kind of flavor of it because it's basically the same. Because now we are talking about spin information, which is the most important part. But of course, there is also can we manipulate the antiferromatic distribution using spin current, which is basically the counterpart of it. And there have been some proposal that it should work also a bit differently, but it should work the same way. Basically, when you shine, you have a spin current which is entering an antiferromagnet, then you will have a torque, which is called spin torque, equivalent to what's happening in ferromagnetic material, but it will count the antiferromatic layer in two opposite ways. Okay? And the way to understand that, it has just an opposite action on the two sublattices, which create an opposite effective torque, typically. So this is exactly what's happening. It has been proposed by Gobenet first. I think it has triggered a lot of things. But what has triggered the community on this, it's a paper on a very peculiar system with some kind of evasion symmetry breaking, but they managed to see some kind of switching of the antiferromagnet by shining a current on it. But now it's been a bit debated, but that really triggered the community. So this is some reference you need to know if you are talking about antiferromatic spintronics. Okay, they've done some stuff more. So what's happening in oxide? Okay, in oxide is not so easy. So first of all, when it's not so easy, we do a bit of simulation and theory. But definitely, what will happen is exactly what's happening here. When you have the spin torque, then they will start counting, okay? And when they count like this, then you create a huge exchange field here. And then this exchange field will take over, and the spin will start processing around this exchange field. And this is the way you will be able to manipulate an antiferromagnet using a spin current. So you use any kind of spin current generator. So this kind, you can play platinum, you apply a current, then you have this torque, and then in this very nice work that has been shown that you can actually reverse the Néel vector by shining tens of picoseconds. So there've been a lot of work doing this. I think this is one of the first one, but one of the main difficulties here, they were shining very large current for a very long time. So nothing compared to 10 picoseconds, and nothing compared. So basically, there was a huge amount of heat in this sample, and then by looking before and after, they could see some change in contrast. So people got excited about this. So there have been a lot of study about that, and I've been two other papers that I'd like to quote because there is non-magnetic origin and absence of evidence. I think it's always very nice to be able to publish a paper, a PRL with absence of evidence. So I think we should always consider this as a possibility. And because what's happening, actually, that was the switching. I do this quickly. It's when you shine a huge light like this, you have also an anisotropic strain. And since NIO, it's also magnetostrictive, if you have an anisotropic strain, so you don't strain the same way in one direction and another, then you will start rotating the T domains, and this has been proven here because what they've done a cross, and then they have just cut out a circle, so you have no current which is flowing here, and they could switch anywhere in the middle, even if there is no flow of spin current. So there was the proof of this. So that's that. But all what those studies have in common is that very large current for a very long time, so a second or milliseconds. So I think I will skip a lot. I want just to give a little bit of advertisement of this one because it's a bit of dreaming, let's say. There is a prediction, because it has been demonstrated in ferromagnet and not yet in antiferromagnet, but if you applied a DC current, you can fully damp anti-damp, sorry, the dynamics in antiferromagnets, and then you can trigger terahertz dynamics. So there will be a possibility to have a DC application of something and generating a terahertz other thing, which is very nice, because it's not so easy to generate terahertz. But in reality, it's not so easy. It has been proven that it works with the IC, for example. Michel told you about that last week. And the threshold here would be kind of high. So you can always go to this paper, which is very interesting. It's a bit cumbersome anyway, but that would be a bit of dreaming. So there is anyway some kind of take-home message, because first of all, working with antiferromagnetic material is nice, but it's quite challenging. And especially, most of the time you work with antiferromagnetic domain in thin layers, which can be quite small, so you need techniques to be able to visualize them. So it's not to be neglected, it's really, we have some effort to put on the way of imaging directly the antiferromagnetic vectors. So it's also the same way, there is a huge work to do to be able to prepare monodomain states, because they are not easy to handle. We cannot handle them with a magnetic field. So it's something which is very difficult, so it's a lot of material science and material engineering. Okay. So the same way, as I said, that we need some advanced techniques, and of course, since antiferromagnetic dynamics require terahertz are in the terahertz, they require experiments which actually are able to probe this ultrafast dynamics. So I come to my conclusion, and so definitely antiferromagnetic spintronics is a field of research which is definitely booming. So there are a lot of things to do. Antiferromagnetics have kind of superior characteristics compared to ferromagnet to some extent, especially when we will deal to sub-terahertz and terahertz dynamics. So there are a lot of very nice breakthroughs. I've tried to give you some kind of a flavor of what we can do with this and what people have been doing. And there are still a lot of things to do. And as far as we are concerned, we are trying to bring our small brick to the wall. And if you want to know more about this, I suggest you to talk to Sanjay, because he will tell you everything about that. Thank you for your attention.